Hi everybody! So today I wanted to make a video of one of the in-person optical mineralogy demonstrations that I do, and in this case we're going to focus on Brazil law twinning in quartz. Last time we compared the different optical behaviors of a piece of quartz and a piece of glass when viewed with a polariscope, and here's a link to that video, Snellius minerals, quartz versus glass in the polariscope. But the Brazil law twinning we saw in our quartz specimen deserves a much deeper dive, and so that's what this video is trying to do. Let's review a few pieces from our previous video relevant to investigating Brazil law twins. Last time, our experimental setup consisted of two samples, one being cullet glass and the other being a quartz crystal with windows cut perpendicular to the C crystallographic axis. And we were going to take a look at the optical properties of these specimens in our homemade polariscope, which consists of a light board as a diffuse light source, along with two pieces of linear polarizers that have been framed. There's also a ring stand, but that's just to hold the camera. Our experiment last time started in a dim room with our light board as our source of diffuse light. We then brought in our first linear polarizer. And what our linear polarizer does is it takes our diffuse light source, which is vibrating in all sorts of different directions, and only allows one vibrational direction of light to pass, in this particular case only allowing light vibrating in an east-west direction to pass through this polarizer. We then brought in our second linear polarizer, oriented so that the vibrational direction it allowed light to pass is perpendicular to our first. By setting up our polariscope in this manner, we are at crossed polarizers, and this effectively blocks out the light coming towards us. However, if we add a mineral sample in between our two crossed polarizers, the crystalline structure of our mineral can reorient the light traveling through our crystal and allow it to pass through our upper polarizer. Here from our previous experiment, you can see the cullet glass to the left is being pretty boring. However, our quartz crystal, which is to the right and has all sorts of rainbow effects going on, is doing something pretty interesting to light. We then brought our camera closer to our quartz crystal in order to investigate further. And right about here you can get a really good view of all these sorts of rainbow triangles going on in our quartz crystal. These rainbow triangles are our Brazil law twins, and the story behind them is pretty awesome. But first we have to talk about a fairly unique property that quartz displays known as optical activity. When we bring our camera even closer to our quartz, we can actually see one of the effects of this optical activity. And that's in the generation of the quartz uniaxial optic axis interference figure. I'm actually going to grab a piece from the educational video Snellius Minerals Interference Figure Projections now to talk a little bit more about this. The left part of this image shows an optic axis interference figure projected for the uniaxial mineral corundum. The right part of this image shows an optic axis interference figure projected for the uniaxial mineral quartz. The main differences between these two interference figures are actually caused by the optical activity of our quartz. With our corundum, you can see our isogyres, the dark bands, meet in the center of the image with a cross. However, with our quartz interference figure, we have a distinct circle of color that the isogyres don't actually end up entering. This bullseye circle at the center of our interference figure is caused by the optical activity of quartz. And this results from a specific feature of the quartz structure. You can think of the quartz crystal structure as containing a spiral staircase. As the plane of our plane polarized light interacts with this spiral staircase, the crystal structure ends up rotating that plane of our plane polarized light. A much better and more detailed explanation for all of this can be found in the article Quartz, a Bullseye on Optical Activity. But I think this is the simplified explanation that will suit us for today. So our quartz generates a fairly unique optic axis interference figure due to its optical activity. Going back to our experiment, you can see that optic axis interference figure here as well. The color of that central circle is going to be based on the thickness of our quartz crystal. The thicker our quartz crystal, the more we can have that spiral staircase rotate the plane of our plane polarized light. Let's move our view around our crystal now and see if we notice anything interesting with our interference figure. Once we enter the different areas of our crystal with the rainbow colored triangles, you'll notice our interference figure gets a bit strange. And what's going on here actually has to do with those spiral staircases we talked about earlier. When you think about a spiral staircase, you actually have two options for how to set up the structure. You can have the spiral staircase spiral in a counterclockwise fashion, or have it spiral in a clockwise fashion. Imagine starting out at the bottom of either of these staircases in this image. As you climb up the staircase, you'll rotate in a different direction depending on which staircase you pick. The structure of our quartz crystal can actually do the same thing. You have two options for the quartz crystal structure, one that rotates clockwise and another that rotates counterclockwise. For some quartz crystals, the entire crystal either is rotating clockwise or rotating counterclockwise. But for this particular crystal, the various rainbow triangles that we see are actually Brazil law twins. These are areas where the spiral staircase in our quartz crystal structure has actually flipped from clockwise to counterclockwise, or vice versa. When looking closely at areas of our quartz crystal without Brazil law twinning, we can generate a quartz uniaxial optic axis interference figure. But when we take a look at those areas with Brazil law twinning, things become much more complicated. The optical activity of our quartz is caused by those spiral staircases in our quartz crystal structure. Looking at the regions of our quartz crystal where those spiral staircases flip back and forth means that the rotation of our plane polarized light is also going to switch back and forth. Under certain circumstances, this would allow us to generate an interference figure known as Aries spiral, but in this particular crystal there's a bit too much going on to generate a nice version of that. The Brazil law twins in our quartz crystal are three-dimensional in nature. And so a way to better understand this is to actually change our viewing angle a bit of our quartz crystal, and you can really get an idea of how these Brazil law twins work. Also, with how thick this particular quartz crystal is, it makes viewing some of the Brazil law twins a bit more difficult since they're really stacked on top of one another. So another way to investigate this is actually to take sequential slices from a quartz crystal and investigate those in our polariscope. So that's what we're doing with the next piece of our experiment here. This is a different quartz crystal of which I've taken a variety of slices so that we can really see more the individual Brazil law twins. And we'll be using our same polariscope setup as last time. We're starting out with a view of our light board. We'll bring in our first framed linear polarizer to act as our lower polarizer of our polariscope setup. Now we'll add on our sequential quartz slices, starting from the bottom of the crystal and building our way upwards. There are 4 slices total from this particular crystal, each with a different thickness, along with sort of the polished end of the crystal as well. However, you can see with our view of transmitted plane polarized light that not really too much interesting is going on with this quartz crystal. It's pretty much just clear. That is until we bring in our upper polarizer and can then explore the optical activity of our quartz along with the Brazil law twinning in this quartz. The thickness of each of our quartz slices is going to determine the color that we end up seeing due to that optical activity. Except where there's Brazil law twinning occurring in our quartz crystal, messing with those spiral staircases in our quartz, and then how that plane of our plane polarized light is rotated. We'll zoom in and we'll start with the most basal section of our quartz crystal, taking a bit closer look here. This slice has just a little bit of Brazil law twinning, and as we get closer you can see a really nice quartz uniaxial optic axis interference figure. Moving on to our next slice, you'll notice that the Brazil law twinning actually gets a bit more developed here, but our optic axis interference figure is still doing pretty well in the areas of the crystal that aren't twinned. Looking at the next sequential slice up our crystal, you can see here that the Brazil Law twins are even more developed than they were in our previous slice, and our final crystal slice continues that trend. The last item here is a semi-polished end of our quartz crystal. You can tell some things are going on there, but without it being fully polished, it's a bit hard to actually make anything out. Now that we've taken a look at the sequential slices through our quartz crystal, let's also investigate how we can figure out which way those spiral staircases in our quartz crystal structure are rotating. We're going to do a speedy version of this today, but a more detailed explanation can be found in Quartz, a bullseye on optical activity. What we're going to do is rotate our upper polarizer here. So we're going to rotate the polarizer in a clockwise fashion, and I want you to pay attention to how the colors shift in our quartz crystals. The sequence of color change here is telling us something about those spiral staircases going through our quartz. We already know that the area of our crystal with Brazil Law twinning is where our spiral staircases are flipping back and forth. Let's focus on some of the areas of our crystal without Brazil Law twinning to make things a bit simpler. If I rotate our upper polarizer clockwise, if our crystal also has its spiral staircases rotating clockwise, the series of colors we see will be red, orange, yellow, green, blue, violet. And if those spiral staircases are rotating counterclockwise, the sequence will be violet, blue, green, yellow, orange, red. Let's focus on our crystal slice in the upper right, which currently is starting out as yellow. And as we rotate our upper polarizer clockwise, we go from yellow to orange to red to violet to blue. For this slice of our quartz crystal, the spiral staircases are for the most part rotating counterclockwise. The Brazil Law twins are where we have a mix of clockwise and counterclockwise, but there's also one little segment in the upper left portion of this crystal slice where those spiral staircases are rotating clockwise. If you're looking at that upper left portion, as we rotate our upper polarizer, you'll notice the crystal goes from yellow to green to blue to finally violet. So that tiny segment of our crystal has our spiral staircases rotating in a clockwise direction, and we can continue to do this exercise for all of our crystal slices. Pick out whichever is your favorite to follow along as we rotate our upper polarizer, and if you do this over and over again, you'll eventually end up with a map similar to the following. This quartz crystal is fairly complicated. Our initial slice is almost entirely of counterclockwise spirals, and as we go through our sequential slices of our quartz crystal, a clockwise portion begins to take over more and more of the upper left of the crystal, in addition to our Brazil Law twins becoming more and more abundant. To recap what we did today, we talked about Brazil Law twinning in quartz. You can think of part of the quartz crystal structure as a spiral staircase. And because our quartz crystals have this spiral staircase, they also have an interesting optical property known as optical activity. This optical activity allows our quartz crystal to rotate the plane of our plane polarized light as it travels through our crystal. This allows quartz to generate a fairly unique uniaxial optic axis interference figure. The spiral staircases in our quartz crystal are also the cause of our Brazil Law twins. The Brazil Law twins are areas in which our quartz crystal structure has switched from having its spiral staircase rotate clockwise to counterclockwise or vice versa. We then investigated Brazil Law twinning in a series of sequential slices through a quartz crystal. This helps to show off just how complicated and beautiful this phenomenon can be, although in the modern day this really isn't as important as it once was. Nowadays most quartz is synthetic if it's used in an industrial application, and with the synthetic quartz you don't really have to worry about Brazil Law twinning. If you'd like to pick up some materials to investigate optical mineralogy on your own, you should check out the eBay store Snellius Minerals. There's a wide variety of very nerdy mineral specimens there, In addition, if you have any specific requests for me or would like to explore a particular educational concept, feel free to reach out to me at snelliusminerals@gmail.com. Here are the references I used in the creation of today's video. Thanks again for watching, and have a great day.